To help us in our probability calculations, we are now going to look at a subject called counting. So as we know, to answer a probability question, you have to do some counting. For example, you remember the problem about rolling a fair die with six sides numbered 1 through 6. If we want to know the probability that the number rolled is greater than 2, we have to calculate a fraction, the number of outcomes where the number rolled is greater than 2, divided by the total number of possible outcomes. So finding both of those numbers involves some simple counting. The event consisting of the outcomes greater than 2 is the numbers 3, 4, 5, and 6. There are 4 objects in that set, so the numerator of this fraction is 4. And the sample space, the set consisting of all the outcomes, consists of the numbers 1 through 6. There are 6 elements in that set, so the denominator of this fraction is 6. And 4/6 simplifies to 2/3. So to do probability, we have to do some counting. In this case, the counting was fairly easy, but there are probability questions where it's not as easy to do the counting. Here's an example where the counting is a little bit more difficult. If you are taking a true-false test with 10 questions, and you're selecting random answers for each of the 10 questions, we might ask what the probability is that you will answer all the questions correctly. Pretty low probability, you would guess, and we will look at this question later in this set of slides. And we'll be looking at other questions like this, where counting the possible outcomes is not quite as straightforward as in the first example that we just looked at. But one thing to keep in mind, the counting won't be difficult once we know how to do it. So all of this counting, advanced counting that we will be doing, is based on what's called the fundamental counting principle. So beginning with an example is probably the best way to go here before giving you the principle. So let's say you order a sandwich and a drink from a small restaurant whose menu has 3 sandwiches and 4 drinks. So the menu looks like this. The sandwiches available are corned beef, pastrami, and ham, and the drinks are coffee, tea, milk, and Pepsi. So you are ordering 1 sandwich and 1 drink, and the question is, how many possibilities are there for your order? Well, here's one way to get sort of a picture of the situation. We could picture your ordering like the possibilities for your order like this. There are 3 possibilities for your sandwich: corned beef, pastrami, and ham, which I've listed here in this row. And with each sandwich, there are 4 possibilities for your drink. So you could order corned beef with any one of the 4 beverages. You could order pastrami with any one of the 4 beverages, and ham with any one of the 4 beverages. So here the orders are grouped into 3 groups, depending on the sandwich, with 4 orders in each group. Our textbooks, both of our textbooks, use tree diagrams for the same thing. So in our textbooks, for this problem, we might see a tree diagram that looks like this. There is a start node. This is like the root of the tree, At this level, the first level below the start, we are choosing our sandwich, and there are three choices: corned beef, pastrami, and ham. And down here at the second level below start, we are choosing our beverage. And a path beginning at start and ending on the bottom level through the tree represents an order. Right? For example, start, pastrami, Pepsi represents the order of a pastrami sandwich and a Pepsi. And both of these ways of picturing the situation are intended to make it obvious that you have three groups of orders, each with four possibilities in it. So three groups of four, the total number of orders is 3 times 4, or 12 orders. And here is the fundamental counting principle, which is sort of a generalization of the example we just looked at. If you are going to make two choices, one after the other, for example, a sandwich and a drink, and the first choice can be made in m ways, and with each way of making the first choice, the second choice can be made in n ways, then the number of pairs consisting of a first choice and a second choice is m times n. So if you're making two choices, one after the other, the number of ways of making those two choices together is m times n. So in our example, there were 3 ways of making the first choice, the 3 sandwiches, so m was 3. There were 4 ways of making the second choice, the 4 drinks, so n was 4. So the number of ways of ordering a sandwich and a drink, of doing both of those things, was 3 times 4. The fundamental counting principle also applies to situations where you are making more than 2 choices. For example, assume you want to order a sandwich, a drink, and a dessert from the small restaurant in our first example. And suppose that the restaurant has three desserts available. So the menu would look like this. Still the same 3 sandwiches, the same 4 drinks, and the menu in addition has 3 desserts. How many ways are there of ordering a sandwich, a drink, and a dessert? Well, we are now making 3 choices, one after the other. We're going to order a sandwich, a drink, and a dessert. The sandwich can be ordered, the first choice can be made. In other words, the sandwich can be ordered in 3 ways. The second choice, the drink order, can be made in 4 ways. And the third choice, the dessert order, can be made in 3 ways. Total number of orders is 3 times 4 times 3. 36 possible ways of ordering a sandwich, a drink, and a dessert. Let's try this example. You are taking a true-false test with 10 questions. How many ways are there of answering all 10 questions? So to answer all 10 questions, we are now making 10 choices, one after the other. The first choice is our answer to the first question. The second choice is our answer to the second question, and so on. So we're making 10 choices, one after the other. There are 2 possibilities for each choice. So the number of ways of answering 10 questions on this true-false quiz is 2 times 2 times 2, and altogether there are 10 2's here, right? One 2 for each of the 10 possible choices. Multiplying 10 2's has shorthand 2 to the 10th, and 2 to the 10th is 1024. Another example. So assume there's a family of 5 people. We're abbreviating the 5 people: M for the mother, F for the father, OS for the older sister, YS is the younger sister, and B is the brother. And we want to choose 3 of these 5 people and arrange them in some order for a photograph. How many possible arrangements are there of 3 of the 5 family members? So we're choosing 3 of the 5 family members and arranging in order for a photograph. So we are going to do the choosing and arranging all together. So the plan is that we are going to make three choices in sequence. We will choose one of the 5 family members to be the first person in line. Second choice will be to choose one of the remaining 4 family members to be the second person in line. And then finally, our third choice will be to choose one of the 3 remaining family members to be the third person in line. So we're making 3 choices in succession. There are 5 choices for the first person in line. Once the first person in line has been chosen, there are 4 choices for the second person in line. And then once the first 2 people in line have been chosen, there will be 3 choices left for the third person in line. So 5 times 4 times 3 is the number of ways of choosing 3 of the 5 family members and arranging in order for a picture. That's 60 when you multiply. So we want to generalize this previous example. So if you have a set containing n objects, in our example, n was 5. It was the 5 family members. So you have a set containing n objects, and you are going to choose R of those objects and put those R objects in order. In the example, R was 3. We were going to choose 3 of the 5 family members and put them in order. Then the number of ways of doing this is you start with 5. That's n. Start with n. You multiply by 1 less. In other words, you multiply by n minus 1. You multiply that by 1 less. In other words, multiply by n minus 2. And you keep multiplying until you have R factors. It turns out that the last factor will be n minus R plus 1, but that isn't too important. The way of thinking of it is you're starting with n, multiplying by n minus 1, and continuing until you have multiplied R things. So in the case where n was 5, we began with 5, we multiplied by 4, and we kept going until we had multiplied 3 things. So this number is called the number of permutations of n things taken R at a time. And the shorthand notation is either subscript P, subscript R, or simply NPR. And it's the second notation that we'll be using in the slides, and it's the notation that's used in our two books. So if we're looking at the number of permutations of 5 things taken 3 at a time, that will appear on your calculator as 5 NPR3. Talking about a TI calculator, for example. On Desmos, the number of permutations of 5 things taken 3 at a time will appear as NPR followed by 5(3) in parentheses. So really the reason for knowing the shorthand and the words permutation is that your calculator uses the shorthand notation, and so does Desmos. So let me just describe briefly how you can get 5 NPR3 on your TI calculator. Once you have that on the display, then you would hit enter, and the calculation would be done. So the first thing to do is enter the 5. And now we have to find the NPR. So you push the math button. You choose the probability menu from the screen that appears. And then from the probability menu, you choose NPR. And finally, you enter the 3. And then you're all set for the enter button on the calculator to have the calculation actually done. Let's just look quickly at how you would do this on Desmos. So you click the keyboard icon in the lower left corner of the window. So you're on the Desmos home screen. Down in the lower left corner is a little icon that looks like a keyboard. You click on that, and a window will open up. And in that window, you click on Functions. And then you click on the Stats tab. And NPR will be in the middle column. You notice there was a slight typo in the last occurrence of the word click. Okay, here's another quick example. Let's suppose that a museum wants to choose 6 of its collection of 20 paintings and arrange them in order in a gallery. How many ways can they do this? Well, they're taking 6 of 20 things and arranging them in order. This is the number of permutations of 20 things taken 6 at a time. I actually did this on Desmos and got 27,907,200 possible ways of arranging these 20 paintings in order. It's true that you could get the answer by multiplying 20 by 19 by 18 by 17 by 16 by 15. We would be thinking of doing 6 things, one after the other. Choosing the first painting could be done in 20 ways. After the first painting is chosen, the second painting can be chosen in 19 ways, and so on. So we would be making 6 choices in succession. And you could do this on a calculator or by hand, I suppose. But I think using the NPR function is faster. If you're taking all of the elements of a set containing n objects and arranging in order, it's simply called a permutation of n objects. It would not be incorrect to say a permutation of n objects taken n at a time, but usually the terminology is just a permutation of n objects. So going back to our family example, if you were going to take all 5 family members and arrange all 5 in order for a photograph, the number of ways of doing this would be called the number of permutations of 5 things. And you could say the number of permutations of 5 things taken 5 at a time, if you prefer. And there would be 5 times 4 times 3 times 2 times 1 of these arrangements, which is 120. On a calculator, you could do it as 5 NPR5. Okay, before we leave this slide, I also want to mention that there is a shorthand for starting with 5 and multiplying your way all the way down to 1. A standard mathematical shorthand. The shorthand is 5 followed by an exclamation point, and this is read 5 factorial. So in a similar way, 7 factorial would be shorthand for starting with 7, multiplying by 6, multiplying by 5, and you keep going till you get to 1. The factorial function is available on your calculator, and you could use it to calculate the number of ways of arranging all 5 family members in order. So one thing to keep in mind that if we're doing a permutation of n objects taken r at a time, you are choosing r objects and then arranging them in order, and each object is used only once. Okay, you're going to try this example. A bike lock combination consists of 3 of the 10 digits 0 through 9 in order. Right, the 3 numbers for a bike lock combination are ordered. Okay, no digit can occur more than once, so we are not allowing repeat digits. So the question is, how many bike lock combinations are there? Well, here again we are taking 3 of the 10 digits 0 through 9 and arranging in order. So this is the number of permutations of 10 things taken 3 at a time. If you think of it as doing 3 things one after the other, namely choosing the first number in the combination, then choosing the second number from the remaining numbers, and then choosing the third from the remaining numbers, it's 10 times 9 times 8, 720. If you use the permutation formula, it's 10 NPR3, number of permutations of 10 things taken 3 at a time. Okay, here is a similar problem. A bike lock combination consists of 3 of the digits 0 through 9 in order. Right, the numbers in a lock combination have to be put in order. Different order gives you a different combination. But now digits can be repeated. So you could, for example, choose a combination 353 or 777 would be allowed in this scenario. How many combinations are there? This is not a permutation problem. We are not taking 3 of the 10 digits. We may take 3, but we may take 2 and use 1 twice, or we may take just 1 and repeat it 3 times. So to solve this problem, we cannot use the permutation formula. Here's a problem where we have to use the fundamental counting principle. So we are doing three things in order. We're choosing the first number in the combination, we are choosing the second number in the combination, and we are choosing the third number in the combination, making three choices, one after the other. The first choice can be made in 10 ways, any one of the 10 digits 0 through 9. The second choice can be made in 10 ways. Repeat digits are allowed. And the third choice can be made in 10 ways. So the total number of biclock combinations is 1,000. Okay, final example. You have 7 books, and you want to choose 5 of them and arrange in order on a shelf. How many ways can you do this? This is pretty similar to the museum problem, where we're hanging paintings in a gallery. We're taking 5 of 7 objects and arranging in order. Found another typo. Had to add an S to the word objects here. So we're taking 5 of 7 objects and arranging in order. We can think of this as making 5 choices, one followed by the other. We choose the first of the 7 books. That can be done in 7 ways. Then we choose the one of the 6 remaining books to be the second book in order. Then we choose one of the remaining books, 5 remaining books, and so on. 7 times 6 times 5 times 4 times 3, for a total of 2,520 different ways of choosing 5 of the 7 books and arranging in order. On a calculator, 7 NPR 5. And let's try this problem. Let's suppose you have 7 books and you want to arrange all of them on a shelf. How many ways can this be done? Well, you can think of this as making 7 choices. Choosing the first book in order on the shelf, that can be done in 7 ways, and then choosing one of the 6 remaining books, and then choosing one of the 5 remaining books, and so on. We're putting all 7 books on the shelf. 7 times 6 times 5 times 4 times 3 times 2 times 1. 5,040 when you do the multiplying. On a calculator, you could do it as 7 NPR 7, number of permutations of 7 things taken 7 at a time. Or you could do it as 7 factorial. Okay, another example. The club has 8 members who we are identifying by their initials, G, H, B, B, and so on. The club needs to choose a slate of 3 officers, president, vice president, and secretary. And the question is, how many slates are possible if no one can hold 2 offices? So here again, we have a permutations problem. We are choosing 3 of the 8 club members and putting them in order, arranging them in order. President, vice president, and secretary. So you can think of this as making 3 choices, one followed by the other. The president can be chosen, if we choose the president first, the president can be chosen in 8 different ways. If we choose the vice president second, the vice president can then be chosen in seven different ways. And the secretary, after the president and vice president are chosen, can be chosen in 6 ways. 336 possible slates of officers. 8 NPR3 on a calculator.